Greetings, everyone. I'm Sharif with my colleague Sama, who shall be taking you through our project, which is about constructive self-supervised knowledge distillation for real-time vocal key identification with nation-aware pitch extraction. This is how a breakdown of how our presentation is structured. About vocal key identification, this involves choosing a key that matches the vocal range and the voice type of the person who is singing. This is usually during musical production and recordings. We found out that traditional methods for vocal identification rely on human judgment, that is listening by ear, and for rule-based algorithm, these require extensive training. This impact causes increased cost, time, and reduces artistic expression. This is some of the related literature about the project. Yakura did find that self-supervised constructive learning boosting identification by 9.12%, which is in line with our project. Then the vocal recognition is still a challenging task because of the voice expressiveness, background noise, and pitch changes. This was noted by Matthews in 2004. And conventional methods depend on human judgment, rule-based algorithm, both of which are either unreliable and unworkable. This was shared by San and his colleague. About the domain problem, here we are having difficulty in identifying singers key during live performance and recordings. For the computational problem, most machine learning models need huge amounts of labeled data to generalize well. But remember, these are always hard to get, and in case you are to develop it, it will require a lot of quite extensive training and a lot of resources. It leads to poor generalization across different vocal styles. In our project, we are addressing it through constructive self-supervised learning, where the model is able to learn by its own uh, by by representing vocal segments with similar embeddings and downfall the similar embeddings. Then you also uh, note that deep learning models like ICNNs are heavy and slow, which makes it hard for them to run in real time without GPU hardware. This leads to delayed prediction that can ruin live collaborations. Here we are addressing it through knowledge distillation, where we shall use the student model, which is computationally effective. Then more machine learning models are trained only on clean or studio recordings. These don't handle messy and natural vocal as well, leading to more prediction errors in real world applications. Here we're addressing it through the connection aware pitch extraction. Some of the research objectives we are having to develop a model that can accurately and robustly identify keys on the system, then to achieve real-time performance for live application, to minimize reliance on a labeled dataset, and to generalize across diverse vocal styles. We developed a model that utilizes constructive self-supervised learning. Then we also deployed a novel knowledge distillation approach to transfer knowledge from a larger teacher model to a lightweight student model, introduced information mode detection to classify phonation types, and we designed a real-time model capable of identifying vocal keys across different singers, music genres. This is just a breakdown of how our methodology, which involve data set analysis, CSV file analysis, audio file analysis. Then we prepared this data and we trained it using self-supervised learning, where we are training the teacher model. And after constructive self-supervised learning, the knowledge from the teacher model was transferred to the student model through knowledge distillation. Then from knowledge distillation, applied phonation-aware pitch extraction, and in the end, the model is able to come up with real-time key identification. This is a breakdown of how our system architecture is. Our system does receive HTTP requests. We used HTML and JS to design the front end. Then through the FlashX API, this was designed to handle the back end. Audio processing, then we normalize the audio as through pitch extraction. Then it goes ahead into the model. The model goes ahead and analyzes the audio, then predicts the key and displays the result to the front end. Our dataset composed of 2,688 WebI files are recorded from 11 male and female professional vocalists. It was characterized into six major parts where we're having musical, MDI, intervals, frequency, timing, and metadata. For the correlation,
Uh, so hello everyone, this is Derek Samuel Joga, and I'll be taking you through output results, the discussions, and other parts of our project. So we trained around 15 models, and we evaluated them. And this is a summary of our training results. So we had the knowledge distillation, foundation awareness transformer, the BLST, attention mechanism, and the contrastive voice encoder, Siamese network, the CNN transformer, the vocal VAE, the graph neural networks, temporal convolution network, and the contrastive audio learning. So the best two models were the knowledge distillation, which had 89.3 final accuracy, and the foundational awareness transformer, which had 85.8 final accuracy, with the worst being the contrastive learning with wave to vec, and it had a 65% accuracy, followed by a temporal conversion network, TCN, which had a 79.4% final accuracy. And in our table, we show the convergence epoch at a point where the early stopping was triggered because these models were not trained using fixed epochs, but rather we used convergence and early stopping, and then the training hours for each with the parameters. Um, the results for the best and worst models, comparing the two, the teacher-student, we can see the teacher-student model in blue with the foundation green, and the VAE in yellow, and the contrastive wave to vec in red. So as you can see, the accuracy, the teacher's accuracy was higher than the student, though they were almost nearly the same because we saw the student retained 94% of knowledge from the teacher, which is very good progress. And then we have the training time comparison that for the four, and the foundation had the highest time, the foundation transformer. And then we also have the F1 score comparison, and the financial transformer outweighed the VAE and the contrastive wave to vec, with finally the model characteristic comparison, where we see the teacher having an of score of around 0.6 and interpretability of 0.2 with an inference of 0.6 and accuracy of around 1.0. Yes, as you can see, comparing all the various models. And next, we came up with the confusion matrices. As you can see, the teacher-student models confusion matrix is way better off compared to the others. You can see it is able to categorize 92% correctly for the model. These are phonation features. We have the model Falesto, breathy, and oppressed, and it only categorizes 3% for false for the model as Falesto, with 4% as breathy and 1% as breast. Yes, and you can see that for the contrastive wave to vec in our bottom right, it categorizes 68% correctly as model, with around 12% and 15% and 5% wrongly, so which was not a good sign at all. So that's why we decided to go with the teacher-student model. And we also performed explainable AI using Sharply features and GradCam features to be able to obtain the feature importance across all the models. As you can see, so we had to understand which features do these models based on to come up to the final prediction. So we realized that pitch mean had the highest importance compared to others, though even low frequencies. These are frequencies which are close to the human ear, and then harmonic ratio. the fundamental form and frequency with the energy, entropy, and the zero crossing rate, they all had an impact, but mainly pitch mean had the strongest impact, since we are always concerned with the minimum frequency of the pitch for the person in order to identify the key, and then also to be able to identify the phonation of that person. The phonation mode we usually mostly based on the pitch. Yes, as you can see how these features impact prediction in our top right, you can see again pitch mean has a high impact on prediction. And then we compare the foundational wire transformer pitch impact on its predictions, since it was also our second best. And we realized that the Falesto was it had a greater impact. And then we also did the harmonic ratio importance across these different models. And we also realized that Falesto had a very big impact. So Falesto affects most of these models. Then we also again came up with the confusion matrices, and we realized they were almost similar, and actually they were similar to the ones we obtained when we were actually training, which was a good sign of progress. So under model selection and deployment, we selected the knowledge distillation because it had a higher trace of around 84.6%, retaining 94% of the teacher, and its real-time capability of being lightweight, and it ensures fast inference for live music applications, as we shall show in our demonstration, and it has a minimal latency that thereby it can easily detect any changes in the voice speech and other changes in the voices. And our IP assets, we had the contrastive self-supervised learning for the vocal key ID, unlike the current ones which usually use supervised learning techniques. Ours adapts self-supervised learning for vocals, and it is able to categorize the similar voices from dissimilar voices. Then the foundational aware pitch extraction, which combines MFCC and a foundation mode detection to filter pitch variations, plus then our knowledge distillation pipeline, which is a real-time inference via an optimized teacher-student model with an end-to-end workflow. Very well detailed. Well, it has two features. You can either browse an audio file or use real time, as you can see here. So first we shall use shall browse for the files, and then we shall go for real time later on. So when you start analyzing, it will prompt to select an audio file. So for simplicity, we shall select a very small audio file. Shall use some of the ones used while training, but you can also use others. So when you come here and select an audio file, you analyze it, and it will be loading, as you'll be seeing. So as it is loading, so that's it. After analyzing, it returns the key with the BPM and all the other features which are necessary which can be extracted from this audio file. This is the full analysis with the pitch tracking diagrams, the waveform diagram, the chromogram, which is based on to identify the key, a spectrogram, the harmonic percussive separation, as you can see, plus the chord progression. So the foundational analysis, we're able to come up to a conclusion that this is a soprano type with a voiced content of 84.4, and it also includes the notes, which it says that audio contains significant vocal content, the vocal pitch varies significantly, indicating expressive singing or speaking. So this is when you record, and then this is our harmonic structure, as I told you, with the chroma distribution. All this coordinates to our goal of returning the vocal key. Then this includes the audio previews and finally our detected key with its pitch range. So when we go for real time, in real time, we start our microphone, and once someone starts speaking, the model, our front end is interacting with the back end, and we are inferring when I increase my voice or if I reduce my voice, and even when I try to change my pitch, you realize our latency keeps on changing and the key keeps on changing according to the pitch I'm in. So this is how the real time works. As we said, our challenge is still with being able to get real time visualization.